Top 20 Bridge Engineering Interview Questions and Answers. Welcome to our comprehensive guide on the top 20 bridge engineering interview questions and answers. Whether you're a civil engineering graduate, job seeker, or professional preparing for your next big opportunity, this video will help you master essential bridge concepts, from structural types and load distribution to seismic safety and modern innovations. Each answer is crafted to give you clear, concise, and interview-ready knowledge. Let's dive into the world of bridge engineering and boost your confidence for any technical interview. 1. What are the main types of bridges? Describe each with examples. The main types of bridges include beam, arch, suspension, cable-stayed, and truss bridges. Beam bridges are the simplest, supported by piers, e.g., Lake Pontchartrain Causeway, USA. Arch bridges use a curved structure for support, e.g., Sydney Harbour Bridge. Suspension bridges have cables hanging from towers, e.g., Golden Gate Bridge. Cable-stayed bridges use straight cables connected directly to towers, e.g., Millau Viaduct, France. Truss bridges utilize triangular elements for strength, e.g., Quebec Bridge. Each type is chosen based on span length, site conditions, material availability, and cost. 2. What factors influence the choice of a bridge type for a specific location? Several factors influence bridge type selection, including span length, geological conditions, hydrology, available materials, budget, aesthetic requirements, and anticipated traffic loads. For example, long spans over deep valleys or water bodies favor cable-stayed or suspension bridges. If the site has soft soil, lighter structures, or deep foundations may be necessary. Environmental impact, maintenance, seismic risks, and wind conditions also affect the choice. Additionally, urban settings may require minimal construction time and visual harmony, while rural areas may prioritize cost efficiency. 3. Explain the difference between simply supported, cantilever, and continuous bridges. Simply supported bridges rest on supports at each end, transferring loads directly to abutments. They are easy to design and construct but not ideal for long spans. Cantilever bridges extend structures from piers without immediate end support and meet at a central span. They are suitable for medium spans, e.g., Forth Bridge, UK. Continuous bridges span over multiple supports with continuous beams, offering better load distribution and reduced bending moments. Each type balances structural complexity, flexibility, and span requirements. 4. What are the common loads considered in bridge design? Bridge design considers several loads: dead loads, self-weight of the structure, live loads, traffic, pedestrians, impact loads, wind loads, seismic forces, thermal loads, and hydraulic forces in case of water crossings. Dead loads are permanent and predictable, while live loads vary with usage. Wind and seismic forces become critical in long-span or tall structures. Thermal expansion/contraction due to temperature changes is also crucial. Proper load analysis ensures structural safety and durability. 5. What is the role of bearings in bridges? What types are commonly used? Bearings allow controlled movement between a bridge superstructure and substructure. They accommodate thermal expansion, shrinkage, seismic activity, and rotation. Common types include elastomeric bearings, rubber layers, pot bearings for high loads, roller bearings permit horizontal movement, and spherical bearings for multidirectional movement. The choice depends on bridge type, expected movements, and load capacity. Bearings improve longevity by reducing stress on other bridge components and facilitating structural flexibility. 6. How is load distribution handled in a suspension bridge? In a suspension bridge, the deck load is transferred to vertical suspenders, which hang from the main cables. These cables are anchored at both ends and draped over towers. The towers transfer the load vertically to the ground, while the anchorages bear the horizontal forces. This system allows the deck to span long distances while remaining relatively light. The load distribution is efficient, making suspension bridges ideal for spans exceeding 2,000 meters, like the Akashi Kaikyo Bridge in Japan. 7. What is the importance of expansion joints in bridge design? Expansion joints accommodate thermal expansion and contraction, shrinkage, creep, and movement due to traffic or seismic activity. Without them, differential movement would cause cracking, joint separation, or structural damage. These joints are placed at regular intervals and typically between spans or at abutments. Modern joints include finger joints, modular joints, and elastomeric strip joints. Proper joint design ensures bridge longevity, smooth vehicle passage, and reduced maintenance. 8. How do you ensure seismic safety in bridge structures? Seismic safety is ensured through flexible structural systems, base isolators, ductile detailing, and energy-dissipating devices. Bridges in earthquake-prone areas are designed with seismic load considerations per relevant codes, e.g., AASHTO or Eurocode, proper foundation design, use of seismic dampers, and adequate reinforcement prevent collapse. Redundant load paths and expansion joints with movement allowances also help. Retrofitting older bridges with modern seismic technologies enhances resilience during earthquakes. 9. What are the causes and prevention methods for bridge scour? Bridge scour is erosion of soil around foundations due to swiftly moving water, weakening structural integrity. It's caused by floods, high river velocity, or changes in water flow patterns. Prevention includes deep foundations, riprap or gabion placement, scour countermeasures like collars and aprons, and regular inspection. Hydraulic modeling helps identify risk zones. Early detection and maintenance are critical to preventing foundation failure and bridge collapse. 10. What materials are commonly used in modern bridge construction and why? Modern bridges use concrete, steel, and composite materials. Reinforced and pre-stressed concrete offer high compressive strength, durability, and cost-effectiveness. Steel provides tensile strength and flexibility for long spans. Composite materials like fiber-reinforced polymers, FRP, are used for corrosion resistance and lightweight applications. Material selection depends on span length, environmental conditions, cost, and required aesthetics. Advanced materials allow longer spans, faster construction, and lower maintenance. 11. What is the difference between a box girder and an I-girder bridge? Box girders have a hollow, rectangular, or trapezoidal cross-section that provides high torsional stiffness, making them suitable for curved bridges or those with eccentric loading. I-girders have an I-shaped cross-section and are commonly used in highway and railway bridges due to simplicity and efficiency in bending. Box girders are typically used for longer spans or more complex geometries, while I-girders are economical and easy to fabricate for standard applications. Box girders often require more formwork and are heavier, but they offer superior aerodynamics and resistance to torsional forces. 12. What methods are used to assess the structural health of existing bridges? Structural health is assessed through visual inspections, non-destructive testing, NDT, e.g., ultrasonic, magnetic particle testing, and sensor-based monitoring systems. Technologies like LiDAR, drones, acoustic emissions, and strain gauges provide detailed data on cracks, deformation, corrosion, and vibrations. Load testing and finite element modeling, FEM, also simulate performance under different conditions. Bridge management systems, BMS, track maintenance, condition ratings, and life cycle data. Regular health monitoring ensures timely repairs, enhances safety, and extends service life. 13. Describe the process of pre-stressing in concrete bridges. Pre-stressing involves applying a precompression to concrete members before they face service loads, using high-tensile steel tendons. The tension tendons compress the concrete, enhancing its ability to resist tensile stresses and cracking. Pre-stressed concrete bridges offer higher load capacity, reduced deflection, and longer spans. This technique is ideal for highway overpasses, flyovers, and long-span girders where structural efficiency is critical. 14. What is the role of piers and abutments in bridge construction? Piers are vertical supports located between bridge spans, transferring loads from the superstructure to the foundation. Abutments are the end supports that connect the bridge to the approach roadway and retain earth behind them. Together, they provide stability, distribute loads, and resist horizontal and vertical forces. Piers often require deep foundations in water or soft soils, while abutments may include wing walls and drainage systems. Proper design ensures longevity, prevents settlement, and maintains the integrity of the entire bridge. 15. How do wind forces affect long-span bridges, and how are they mitigated? Wind causes lift, drag, and oscillation in long-span bridges, especially suspension and cable-stayed types. These forces can lead to vortex shedding, flutter, or galloping, causing fatigue or even collapse, e.g., Tacoma Narrows Bridge disaster. Mitigation involves aerodynamic deck design, wind tunnel testing, dampers, and stiffening trusses. Structural elements like guide vanes, tuned mass dampers, and aerodynamic fairings are used to reduce vibration. Codes require dynamic analysis of wind effects to ensure safety and serviceability under extreme conditions. 16. What software tools are commonly used in bridge design and analysis? Common software includes SDAD.Pro, Midas Civil, SAP 2000, CSI Bridge, RM Bridge, and Luces. These tools support finite element modeling, dynamic analysis, load rating, and structural simulation under various loads. For drafting and documentation, AutoCAD and Revit are widely used. BIM, Building Information Modeling, tools help with design coordination and clash detection. Software selection depends on bridge type, complexity, and design codes. Advanced tools improve accuracy, save time, and support compliance with local and international standards. 17. How is the load rating of a bridge calculated? Load rating evaluates a bridge's capacity to carry specific vehicle loads safely. It is calculated using analytical models, incorporating material strength, geometry, live load effects, and condition of structural components. Methods include allowable stress rating, ASR, load factor rating, LFR, and load and resistance factor rating, LRFR. The most current AASHTO method. Engineers compare actual capacity against standard design vehicles, like HS-20 or HL-93 trucks. If ratings fall below minimum thresholds, posting signs, strengthening, or replacement may be required. 18. What are cable-stayed bridges and how do they differ from suspension bridges? Cable-stayed bridges use cables directly connected from towers to the deck in a fan or harp arrangement, efficiently transferring loads to the towers. In contrast, suspension bridges use cables draped over towers with hangers supporting the deck. Cable-stayed bridges are generally more cost-effective and stiffer, making them suitable for medium to long spans, up to 1,000 meters. Suspension bridges are used for longer spans, over 2,000 meters, but require large anchorages and are more flexible under loads. 19. What are the key steps involved in bridge construction? Bridge construction involves 1. Surveying and soil investigation. 2. Design and planning. 3. Site preparation and foundation construction. 4. Substructure, piers, abutments construction. 5. Superstructure erection, girders, deck. 6. Installation of bearings, joints, and railings. 7. Deck paving and finishing. 8. Inspection and load testing. 9. Opening to traffic. Safety, environmental management, and quality control are maintained throughout. The construction method, cast in situ, precast, incremental launching, depends on site constraints, bridge type, and span requirements. 20. What recent advancements or innovations have influenced modern bridge engineering? Recent innovations include high-performance materials, e.g., UHPC, FRP, modular construction, accelerated bridge construction, ABC, techniques, self-healing concrete, and smart monitoring systems. 3D printing and BIM enhance design accuracy and collaboration. Drones and AI-based inspections improve maintenance and safety assessments. Sustainability through recycled materials and energy-efficient designs is gaining importance. These advancements lead to faster construction, longer service life, and improved resilience against climate and seismic challenges, reshaping how modern bridges are built and maintained. Thanks for watching our breakdown of the top 20 bridge engineering interview questions and answers. We hope this guide helped strengthen your technical foundation and interview skills. If you found this content helpful, don't forget to like, subscribe, and share with fellow civil engineering aspirants. Got a question or want another topic covered? Drop it in the comments. Until next time, keep building your knowledge. Brick by brick, beam by beam.